Hey guys, welcome back to Introduction to Computer Networks. This is Polly speaking live again from National Taiwan University. Hi Zhixiang and hi all of you. Alright, you see, this is week 9 already. Hi Amy, Noe, Junhuan. By this Saturday, we again have several assignments due. One is PA. PA6 is straightforward. If you find PA5 easy to handle, PA6 should be straightforward. And there are 4 quizzes due this week as well. Among them, 23 and 25 are straightforward. And 25 is a new quiz. Okay. 24 and 26, these two are a little bit tricky. You want to get your teammates next to you, and you guys might need to brainstorm a little bit. All right. Yeah, good to see you, Ming Huang, Yan Jia, and Ali. All right, so let's check out the topics today. Yeah, it's going to be, well, in fact, the whole week is going to be about TCP's reliable data transfer mechanism. Okay. In this first overview video, you will hear that in 3 parts. First part, Polly is going to tell you what are the topics, okay, this week. First is introducing the TCP packet format. Second is TCP's reliable data transfer mechanism. Third and fourth are 2 additional mechanisms to support the RDT mechanism in TCP. In the second part of the overview video, you will hear 2 notions that actually work differently from the same notions that we talked about, but in pipeline RDT and RDT 3.0. So these 2 are, first, the sequence number. You see, when we were talking about pipeline RDT and RDT 3.0, there's sequence number. 1 packet, 1 sequence number, and it's incrementing by each packet. So sequence number 1 for packet 1, sequence number 2 for packet 2. The sequence numbers are counting the data by packets. But in TCP, the sequence number is counting data in a different unit. Okay. Second of all, in the general RDT mechanism, we have 2 nodes, sender, receiver. Sender sends data to the receiver. So we keep it unidirectional for the sake of simplicity. Recall? That is to make it easier to draw the finite state machine for the RDT mechanisms. Okay? But in TCP, hey, in reality, 2 nodes, they could be sending data simultaneously in both directions. Think a web client and a web server, right? Web client can be pipelining the request while the earlier request is replied is on its way back. See? Both directions having data simultaneously. So in TCP, data goes full duplex, okay, both directions. So these notions in TCP's RDT are being used differently than the RTTs we've introduced generally. In the final part, you will hear also Polly introducing new terms, particularly this term called MSS. Okay, so pay attention. Okay, follow the video if you can. Towards the end, after the video ends, Polly is going to ask you to type up what MSS stands for in the chat room. All right? So here's the first video. It's a little bit long, 6.5 minutes, because there are 3 parts in it. And this is 3.5, connection-oriented transport, particularly the TCP protocol. So in this particular section, we're definitely going to talk about the RDT implemented in TCP. Now, provided the background, okay, very extensively in 3.4, you should be able to understand TCP's implementation of RDT, TCP's design of RDT. Now, in addition to the RDT in TCP, we are also going to talk about the packet format of TCP. And that is what the segment structure meant here by the textbook authors. And then there are 2 minor functions, but necessary functions in TCP. One is called the flow control. The other is called the connection management. And this is the overview. TCP we know already. Just like UDP, it's what? End-to-end process-process communication. So end-to-end there can also be referred to as point-to-point communication. We have a sender process and the receiver process. Now, in this connection here, what we're doing is to do reliable and in-order data transmission. Now, what's a little bit unusual when we talk about TCP is this. Instead of earlier, when we were talking about the general principles of RDT, we are counting the data by what? Packets. Packet 0, packet 1, packet 2, packet 3, so on and so forth. But in TCP, we count data all right, but we count the data by the bytes. Byte 0, byte 1, byte 2, and so on and so forth. So that connection here, when we are passing data around, we're actually passing a stream of these bytes. Right? So there's no more message boundaries, or there's no more packet-to-packet separation. Right? And last, this is actually telling you ahead of time that TCP's reliable data transfer is doing this, the pipeline-based RDT, so that we have a window size there, where the size n is definitely larger than 2. And so we could have multiple packets in transit so that the utilization of the connection there can be higher. Now, what we don't know quite yet is this. This window size is also used not just for reliable data transfer. Later on in section 3.6 and 3.7, you will also hear it's also for the congestion and flow control. Okay, so there's going to be a window size for flow control, and the window size for RDT is also used, okay, for congestion control. And conveniently, in flow control, what's being done is the receiver will every now and then tell the sender, hey, you might want to slow down or you might want to speed up depending on how much the buffer space is occupied at the receiver side. You see what happened at the receiver end of the TCP is this. Data will come in continuously from the sender. Data will be extracted and passed up to the application layer process. So there's an incoming rate and there's also an outgoing rate. When the outgoing rate is slow, incoming rate is fast, then you see the buffer space is quickly exhausted. Okay, so at that point, receiver tells the sender, hey guys, slow down. All right. Now, the other way around, if the buffer space is very empty, then telling the sender, feel free to send more. So flow control there. Okay, mainly allowing the receiver to tell the sender, hey, slow down or speed up, such that there's no congestion occurring at the receiver side. Because if the incoming rate is high, outgoing rate is slow, over time, when the buffer is exhausted, the incoming data will be what? Will be dropped. Okay, so delay long, and you see also data loss there, right there at the receiver. So this is to avoid also congestion, but it's a bit weird. It's actually to avoid congestion at the receiver side, not quite in the middle of the internet. Okay, so when I say in the middle of the internet, I actually meant congestion in the core of the internet. Sender process, receiver process is what? At the end of the internet, at the edge of the internet. So flow control there is to try to control the end processes such that there's no packet drop at either end. Congestion control, on the other hand, is to control such that there's no packet drop or congestion in the middle, in the core of the internet. And TCP being connection-oriented transport layer service is sending some messages at the beginning before data can be transmitted. So there are some handshaking being done right before the data exchange. And these handshaking messages are there to set up the initial states of the sender and receiver. And that is called the connection management part of TCP. Last but not the least, there's a mindset change here in a TCP connection. Data traveling in a TCP connection is now full duplex. What I meant by that is the data flow is going, bidirectional. Okay, so two processes or point-to-points will be sending data this way as well as this way. Now, why is this a major mindset change? If you recall in 3.4, when we were talking about these reliable data transfer mechanisms, we always say what? This is the sender side of RDT, and this is the receiver side of RDT. What we are saying there implicitly is also, this is data sender side of RDT. This is the data receiver side of the RDT. Data receiver there, receive data. It transmits something as well, but it's transmitting only what? The feedback messages, the ACMEX messages. The receiver there does not send data. So TCP here you see being more general. Data can go either way. So the two processes will be implementing both the sender and receiver finite state machines. And the last bit is this. Yeah, MSS, a special term that is referring to this, the maximum segment size. If you recall, a packet at the transport layer is called a segment. So maximum segment size is essentially the maximum packet size. Okay. Yeah, in reality, in actual TCP implementation, we're still sending data packet by packet. But the sequence number, okay, we'll be checking to do reliable data transfer is now counting the bytes, okay, of the data, not the packet numbers of the data. All right, guys, what is MSS? Can you spell it out? Okay, do it on the, in the chat room, please. Very good, Ryan. Thank you. There you go. Yeah, it kind of tells the internet delay from my end to yours, and I can see that from different students, the delays are a little bit different. So Ryan, you're probably on campus, okay, and very close to me. All right, so chances high that is you are probably in the EECS quartet here, okay, this area. Yeah, you are on campus. Very good. Okay, max packet size, exactly. Okay, Cassandra, you've also paid attention and interpreted. Segment is the packet in the transport layer. Very good. And hey, with the segment explained, hey, the next topic is to introduce the TCP packet format. So in this video, you'll hear two parts again. In the first part, you hear Polly compare and contrast UDP packet to TCP packet, particularly the header of the two packet types. In the second part, Polly will be spending some time talking about specific fields in TCP packet header. There are some special bits, okay? If you flip the bits on, it indicates the packet, the TCP packet is a certain type of TCP packet. For example, an add packet, a data packet, a control packet to do the connection setup, for example. Okay, so there are several bits there, okay, allowing flags there, allowing you to set the packet type. And then very importantly, the sequence number and the ACK sequence number fields. So the sequence number field is for counting data. The ACK sequence number is what? To acknowledging data. Okay, so in the TCP packet header, you have both the sequence number and the ACK number. Okay, so TCP packet format. TCP segment structure, aka the packet format. It does look a bit complicated, definitely more complicated than the UDP packet. If you recall, in UDP, we do have these fields: source port number, destination port number, as well as the checksum. Okay, so all these are what called the header fields. So in TCP packet, the header part is substantially larger. While the data part, it's still variable lengths that could be large, could be small. Oops, yeah. So the overall structure in TCP packet is actually very similar to UDP, two parts, header and data. The main difference is where? The header part. Okay. So some of the header fields repeat itself. We see source port number and destination port number as well as checksum also in TCP packet header. But what else in the UDP packet header that we don't have or we do have in TCP's packet header? And here's UDP's packet format. So we do see source port number, destination port number, checksum. And what else is in UDP's packet header? The length. So that is the entire packet size, including the header as well as the bytes in the segment. So data and header together, okay, in this field, the length. Do we have lengths in TCP's packet header? We actually don't. The thing that we have the closest is this, the header length. So the length in TCP packet header counts only the size of the TCP packet header, while the length in UDP's packet header counts the entire UDP packet. Given that we're already talking about the header lengths, why don't we talk about these special bits, okay, special flags in the TCP packet header? First is the A flag. Okay, so this is called the ACK flag as well. When it's turned on, when the ACK flag is on, that's indicating that the acknowledgement number here is actually Valid, meaning that the sender of this packet is trying to tell the receiver that it's trying to acknowledge certain bytes being received. And these three R, S, and F bits, they are there to indicate packets being used to do connection management. So for example, SYN here, the SYN packet is to set up connections. The FIN packet, which is Latin for the end, yeah, conveniently, okay, is to tear down a connection. RST, or the R bit here, means reset, that is to re-establish the connection, to re-initialize certain parameters between the sender and receiver of a TCP. And P bit, yeah, P stands for push, that is to push data now. So this is to actually pass the data out as soon as possible, but it's generally not used. Just like the U bit, this is urgent, so this is indicating that whatever data is here is urgent. So pass it out through the network or to the application layer as soon as possible. Okay, so you see urgent, the purpose, and push, somewhat similar. The ambition of the network engineers much early on is also that hopefully a data network or the internet can also allow urgent data being sent, just like we could make it 911 call, or in Taiwan 110 call to get police's attention or the fire department's attention as quick as possible. But unfortunately, the way the internet is designed is just not very good for urgent critical data transmission. And yeah, we said that these are not used, so there are a number of bits not being used. But the fact is actually there are two more bits being used. It's called the C bit and the E bit. Now these two bits are not really for reliable data transfer service, not for connection management purpose. They're actually there for congestion control. Okay, but it's not quite the congestion control implemented in TCP though. Okay, it's just that the engineers are expecting, okay, later on TCP's congestion control can be extended, okay, together with the core of the internet such that we could do better control. So there will be two more bits we'll have to talk about, but it will be at the end of chapter 3. And that takes us to, yeah, the urgent data pointer. So this is actually working with the urgent bit. When the urgent bit is on, then the transport layer of TCP is going to look into this pointer and then grab whatever the data that's here indicated by the pointer. So this data here will be extracted and passed out as quick as possible. And receive window here. Yeah, this is the window size for the flow control. Okay. If you recall earlier in the overview, yeah, we say flow control is for the receiver to tell the sender, hey, slow down or speed up. And when the slowdown is to be communicated, receive window here will be a small number. If the receiver wants the sender to speed up, the receive window there will be larger. And the last two fields in the header are these. Yeah, the sequence number as well as the acknowledgement sequence numbers. So these are exactly for the reliable data transfer purpose. But keep in mind, we're now counting the bytes, okay, not packets. All right, so that's the packet format. Next is the mechanism, how TCP changes the sequence number to count data by bytes. Okay, so right after the first video, which talks about the mechanism, we'll go over an example. And after that, quiz 23 is coming right up. So pay attention to these next two videos. TCP sequence number and ACK numbers, these are very important fields. Let me elaborate more here. First, the sequence numbers. So what the sequence number says in the packet header is to tell you this: the byte stream number of the first byte among all the data bytes in the packet. So, but what is the byte stream number? Yeah, let me explain. This is the original message, which can be really large, generated by the application layer process. Now, as it's pretty long, right? Each byte can be indicated in sequence in byte stream number. So this is byte 0, byte 1, byte 2, byte 3, byte 4, and so on and so forth. So these numbers, these serial numbers, are the byte stream numbers. So when such a message arrives at the transport layer, the TCP sender is going to what? Break them down into smaller parts. Let's assume that in the first segment, it contains only 3 bytes of the data. So in the header here, the sequence number is going to be what? Oh, the byte stream number of the first byte of data, which is 0. For the second packet, in the header sequence number field, what should be the value? It should be the byte stream order of the first byte of all the data, right? So 3 here. Okay, so that's what sequence number meant. And it tells you where the first byte of this data packet is in the original message. So we could track whether all the bytes in the original messages are being transmitted successfully. Second, the acknowledgement number. Now to explain this, let me tell you, TCP implements, just like go back in, cumulative acts. So that number there, based on your knowledge of go back in, should indicate what? The last byte of all the data received correctly at the receiver and in sequence. But, well, it's actually not quite. So TCP's acknowledgement number is actually counting 1 byte further. So it's the next byte the receiver is expecting. So that number is the number of the next byte the receiver is expecting. Therefore, it will also be the what? The sequence number of the next data packet coming from the sender. And with that said, many of you will probably guess that TCP's reliable data transfer mechanism is similar to go back in. You are actually correct. So let me borrow the diagram that I've been using to explain the sender side behavior of go back in here. The only difference is just that previously, now each rectangle indicates a packet, but now we are counting bytes instead of packets. So each of these are what? Bytes. So we have green bytes, yellow bytes, blue bytes, and gray bytes. But similarly to go back in, the green bytes are what? The bytes that are already sent and acknowledged. Yellow ones are the bytes sent and not yet acknowledged. Blue bytes are those usable, so if there are more data the application layer process wants to send, we could now turn these blue ones to yellow. So usable but not used. Gray ones, not usable because it's what? Outside of the window size, outside of the window limit. Now, the sender generates a data packet. What's going to be in the sequence number is what? The first byte of the data and the byte stream number of it. And if an acknowledgement is coming back to the sender, acknowledging this packet, the acknowledgement number here is going to indicate what? The byte stream order of the next yellow packet. So this first one here is going to turn green. Yeah, so add number here is the first yellow next. And the last bit here is again about TCP's RDT being very similar to go back in. So if you recall, go back in's receiver, when it receives out of order packets, what does it do? It drops all the out of order packets. Now that is actually a wasteful use of network bandwidth, isn't it? So TCP here allows a bit more flexibility. The programmers themselves can decide whether to buffer the out of order packets or to drop them. All right, so sequence number is the first byte of the data in the packet. Acknowledgement is to tell the sender what is the next expected sequence number, which means it acknowledges all the bytes before that number. And TCP, you see it's go back in. But it's not exactly go back in, because go back in doesn't buffer out of order packets at the receiver. But TCP implementers very often buffer these packets. Okay. Now let's try to exercise the byte count mechanism with an example. And this example is a telnet exchange. Now let's exercise what we learned about the TCP sequence numbers and ACK numbers using a simple telnet scenario. The setting is this. We are here at host A. We've already started the terminal and it's connected to the remote machine, host B. So what happened in the telnet is this. When we hit C, a key locally, okay, so user type C, what happened is this. Host A sends a byte, that character C, to the remote machine. Now the remote machine is going to receive this and see what to do with it. Okay. Now, because it's a very straightforward character C, not like escape or control C, therefore what it does is going to be simply echo back the character C to the local host. So host A here will receive the echo C and then display on the local terminal. So once again, host A here has 1 byte to send. Host B here has 1 byte to send. And that's the scenario. Now, the 1 byte of data generated by the telnet process. As soon as it arrives at the transport layer, we're going to add header to it. So sequence number, ACK number being added to it. And the data is simply a character C. Now, when this packet arrives at host B is going to what? Yeah, echo with the same character C. And in the meantime, acknowledge receipt of the data packet earlier. Right? So what will be the sequence number and ACK number will be generating? Well, we send 1 byte of data. What should be the sequence number there? Well, go back here. The ACK number is indicating what is the next sequence number. Yeah, the sender of the ACK packet is expecting. Therefore, sequence number we know should be 79. Now, what should be the ACK number here? Well, ACK number is what? The last byte received and then counting further by 1 byte. What is the last byte received? Yes, 42, because there's only 1 byte. And counting further, yeah, we say ACK 43. And this is also host B telling host A what is the next data byte expected. And therefore, we see the next packet coming back from host A, sequence number 43. But host A here is not echoing C anymore. All it needs to do is to what? Acknowledge receiving this packet. Right? So ACK packet needs to be what? Last byte received by host A, which is 79 because there's only 1 byte. And counting further by 1. Therefore, we get 80. So you see, quite obviously, in order to find out what is the next sequence number, look at the packet coming the other direction's ACK number. In order to find out what is the ACK number, look at the packet sequence number coming the other direction. Similarly, sequence number here, look at the ACK. The ACK number, look at the sequence of the last packet coming the other direction. All right, are you ready for quiz 23? Yeah, so let's exercise by counting, all right? So what you're seeing here is two scenarios, two examples. Let's focus on the one on the left. Okay, we have data only going one direction from A to B. All right. And so here we start from sequence number 100 and we send data 8 bytes. This one being the receiver, of course, acknowledge receiving that packet. And the ACK number will be what? The last byte will be 108. Well, actually, the last byte will be 107. And you plus it by 1. And in the meantime, telling what the host A sequence number should be sending the next data. So the seek of the next packet is the ACK of the previous packet. Okay. Now this seek is 108 and carrying 12 bytes. The ACK going back is then 108 plus 12, 120. Okay, straightforward. This is the one unidirectional case. Now, for quiz 23, I ask you to solve a more complicated case. It's bidirectional. Data can go either direction. And this is the exchange. A started by sending a packet starting sequence number 120 and size 20 bytes. And it's also telling B, oh, if B, you want to send some data to me, I'm expecting 100 to begin with. All right, so host B here sends something back. Okay, it carries data and it, in the meantime, needs to acknowledge this packet. So this value and this value needs to be determined carefully, okay, in order for the TCP to work. All right, and the exchange will go on, okay, for 2 more packets. So can you tell me the value of A, B, C, D, E, F? Okay, that is what the quiz 23 is about. Let's move to the score channel W9 quiz 23. All right, guys, you don't need to be super fast. Okay, think it through. you have 4 minutes to type up what your answer is. And I'm not looking for fast solvers. However, okay, if you are fast and telling why you come up with the numbers, you get the bonus. Okay, so essentially bonus goes to the one with elaborated solution, not just giving me the numbers of A, B, C, D, E, F, but also telling me how you come up with it. Okay, and the fastest of the one telling me how you get it gets the bonus. All right, a little bit tricky this time. So 4 minutes, take your time. Oh, wait, guys. Wait. I actually find some inconsistency, guys. Sorry, team 13, team 8. No, so the question, the quiz 23 on the score channel W923 is incorrect. Sorry, let me replace this. Okay, my bad. Okay, let me change this and upload the real quiz. Sorry. Yeah, because then you see that the one that I was showing right previously here is different. Yeah, there. This is it. Okay, 13 and A. Try it again. Okay. So teammates cross-check each other's solutions. Okay, Yuan Hao, I think the last value, F, is not quite correct. Okay, but on the other hand, Bo Yun here is helping you explain how you come up with the values. Okay. And Zhixiang is the first one to provide how you come up with the values. Very good. Okay, and today the bonus goes to Zhixiang, team number 10. Okay. Bo Yao is also good. No, very good. Bullseye. Tasha, very illustrative explanation. Very good. Wonderful. Hanzhen. Okay. Yujie. Perfect. Ali, great job. Yanjia, you are correct. Zhuxun, also correct. Okay, I see you in how. Okay, editing the solution. Perfect. Perfect. Cheng'en, Ryan. Wonderful. Okay, so Zhixiang is the one receiving the ultimate bonus, but I think those who provided the duration. So let me also add bonus to you guys. Great job. Noe, great job. Tasha. Yeah. Okay, Noe. A cheer for the whole team, right? Wonderful. Okay. Do you see that getting the answers right, of course, it's great. But knowing how you get it right is even better. And that's how you go a long way. All right? So, hey, this is not to say that the grades are not important. The grades are still important. But you want to make sure that you learn something on top of earning good grades. Okay? If you are getting good grades but you don't really get it, that's not good either, isn't it? But if you you learn things but the grades are not good, you know what? You're gonna do fine. You're gonna do fine. Just don't fail yourself. All right, great job, guys. Let's go on. Okay, TCP's reliable data transfer. You know what? I think last week there was a student asking, how do you set the timeout interval for go back in? And today you just heard TCP is very much like go back in. So how do we set up the timeout interval for TCP, a kind of go back in? So in a way, today, these two videos together explains, okay, or answers the question from the student last week. Okay, so the answer is actually a little bit long. Sorry, guys. It's gonna be in two videos. In the first part, I would repeat again. If you set it too short, not good, because you get premature timeout. Last week, we recall, if the timeout is too short, then the sender keeps retransmitting for no reason. Hey, the egg eventually comes back. So that retransmission is just redundant and a waste of bandwidth, right? So you don't want the timeout interval to be too short. But if the timeout interval is too long, hey, some of you don't like when we receive a corrupted egg or receiving an egg saying that the data packet is corrupted, right? And we do nothing in RDT 3.0. Why? Because you wait longer. You could have retransmitted quickly the packet again, but we need to wait longer. So if the timeout interval is too long, it's not good either, because we will need to wait long. So too long, too short, neither way is good. How do you find that balance in the middle? Okay, it's actually hard. Okay, but you know what? We could learn from how TCP does it. Okay, TCP is a real RDT mechanism, and so the first part of the video you will hear Polly saying why setting it the interval too long, too short is not good. And in the second part, the trick in order to not set the interval too short is to make sure you know the round trip time well, isn't it? You definitely don't want to set the interval being lower than the round trip time, because then you will always retransmit for no reason, consistently getting premature timeout. So get your round trip time and make sure the interval is higher than the round trip time. Okay, so the second part, you hear how TCP measures round trip time, estimates round trip time. Now, with the fundamentals of TCP packet format, TCP being bidirectional, and we're actually counting bytes instead of packets. So with these out of the way, we can now come back to talk about the reliable data transfer mechanism implemented in TCP. Before Polly shows you the finite state machine of TCP's RDT, let's define this thing first. It's called the timeout interval or timeout value. Now, TCP being implementing a reliable data transfer protocol, it needs to also define this thing clearly. What is that? If you recall back and go back in, we said that after packet gets transmitted, we start a timer. That timer is going to tick, tick, tick. If an ACK does not come back before that timer expires or that timer times out, then what? We retransmit packet. So this timer there is to allow us to decide whether a packet is lost inside the network. So it's part of the RDT mechanism that is very critical. And that interval determines how long the retransmission is going to go. And that influences the performance of a reliable data transfer. We know already in some earlier example, if that timer is set too short, so packet can sometimes travel the internet a bit longer than usual. If that timer is too short and expires, then retransmission right before ACK arrives back, then this retransmission there is unnecessary and premature. Okay? That is not a good thing in terms of bandwidth consumption. So, not good. If that timer is too long, the intuition also says it's going to take a long time for the sender to discover there's a packet loss and try to recover from it. So you see that the user experience with sending data over this connection is not going to be good. Okay, so slow reaction to packet losses. Either case, not good. So how do we find a balance? How do we set or how do we estimate the timeout interval? You see, it's not that far-fetched. You heard Polly saying this already. The interval should at least cover what? The time data travel to the receiver and the ACK coming back from the receiver. And we know this is called what? The round trip time. But you also heard Polly saying that sometimes it takes longer for the data or ACK packet to travel the internet. Therefore, the timeout interval there should be set to cover longer than most of the round trip time that the pair of sender-receiver might experience. And that is the idea behind how TCP estimates the timeout interval. And you see also, in TCP, it needs to observe the round trip time repeatedly in between the pair of sender and receiver. Right? And this is exactly how it's done. Okay. For a pair of data goes out and the ACK come back, it calculates the time differences between receiving of ACK to the sending of data, and we get a sample RTT. Now, there will be a lot of these sample RTT for each data and ACK pair, but we'll ignore the data ACK pairs due to retransmission. So some of these data might get lost and therefore they get retransmitted. When we receive an ACK for such a data, it could be a bit confusing, right? What is the right data sending time to subtract in order to be sure that this is really estimating just the round trip time and not covering a premature timeout, things like that. And we get lots of these sample RTTs, and they could vary quite a bit. So you see that it's actually not good to use the sample RTT as the timeout interval for the next packet. Not good. So what TCP does next is this, to get a smoother estimation of the round trip time. Okay? And that is done by taking the average of multiple recent sample RTTs. All right. In fact, getting the average is still not good either, right? Because average means somewhere in the middle. So you will have half of the time we have the sender experiences premature timeout. So you want to calculate the average and then add a margin, okay, considering the deviation of the round trip times, okay, such that in the end you get the value, the probability of premature timeout will be as low as possible. Okay, so that's the second part of the video. And sorry, today we'll run over a minute. Okay. So what Polly brings up here is essentially the line of code in TCP's implementation, estimating the smoothed RTT. So the estimated RTT, this variable is to refer to the smoothed RTT. Now the smoothed RTT next is going to be the smoothed RTT now and take a weighted sum of that to the current sample of RTT. Okay, so current smooth RTT, and take the weighted sum of that to the current sample RTT. Okay, so we're taking the history into consideration, that's why it's called the moving average, and we're using a special factor alpha here, so it's a weighted moving average as well. Now the reason that it's called exponential is because of this, right? So the whole thing is the current, okay, smooth RTT. Now this whole thing is going to be used as what? The first term of the next estimation. So you see, okay, the current smooth RTT is going to be weighted what? 1 minus alpha, actually, 2 times. So the current estimated RTT 2 rounds later will weight exponentially less. Okay, 3 times 3 exponents less, 4, and so on and so forth. So the past sample, the influence of it will decrease exponentially fast. Okay. Oh, and by the way, alpha is only 0.125. That is because, we don't want to weight too much on the instantaneous RTT because otherwise it will be what? Also fluctuating. Okay, not exactly smooth. And here shows, the instantaneous RTT and the estimated RTT, the smooth estimation, how they look like relatively. And this is actually actual measurement between UMass and Eulercom again. So the blue one that fluctuates more, like these. These are the instantaneous RTT, the sample RTT. The pink one then is the estimated RTT, the smooth, the average RTT over time. So you see that although the blue one fluctuates a lot, but the pink one, relatively smooth. And you see also, generally as time goes along, the round trip time tends to be longer. And so you see the pink here, the smooth average RTT is tracking the increase of the RTT relatively well. But be careful here. The estimated RTT is definitely not quite yet the timeout interval used by the TCP. Because if you do, you see these guys here, the round trip time is actually way longer than the timeout interval. So for all these guys, you will get premature timeouts. So the estimated RTT there is certainly not covering most of the round trip time observations. So there's more. Therefore, in TCP, the timeout interval is the estimated RTT plus a safety margin. So estimated RTT is the what? The average. And the timeout interval should be the average plus a safety margin there, such that all these sample RTT fluctuates in the middle will be covered. Or, the more sample RTT being covered by the safety margin, the better. Challenge next is to set the safety margin. And the thinking behind setting the safety margin is this. If the sample RTT fluctuates a lot, we use a larger safety margin, right? Small fluctuation, smaller margin. Therefore, the key is to estimate the variation of the sample RTT. So the challenge boils down to estimate the variation of sample RTT. And that can be done this way. So sample RTT is the instantaneous RTT. And estimated RTT there is the variable storing the average RTT. So the deviation is essentially what? The sample RTT subtracting the average RTT. Right? Now, of course, we will not be using this, by itself to set the safety margin because this is also what? The instantaneous deviation. Right? So let's estimate the smooth deviation of round trip time, by the EV-RTT, and borrowing again the technique, the exponential weighted moving average, to get the smooth depth RTT. So the next depth RTT will be the current depth RTT and the weighted sum of that to the instantaneous deviation of RTT. Alright, so the only thing left is just the beta factor, and it's also set to a small value so that we weigh less on the instantaneous deviation. As to why it's 0.25, not 0.2, not 0.125. These alpha beta values are usually given because people have been using these values and they seem to work out fine, and engineers later on will just borrow using the same setting. And now finally, the timeout interval. It is the estimated on-trip time plus the safety margin, which is determined by the deviation of round-trip time. Now, as to why 4 times the deviation of round-trip time, the original designers of TCP, they don't usually talk about this. I mean, the 4 could be a result of repeated experiments, but Poly guessed also it could be because of this. They have assumed the sample RTT distribution being normal. If you recall back in Statistics 101, right, normal distribution is for a sample such that if you plot the histogram of that sample, you see a bell shape. The average is usually in the middle where there are lots of samples, and the 2 ends, few samples. In normal distribution, starting from the average, if you add 2 standard deviation, subtract 2 standard deviation, it should cover what? 95% of the value range of all these samples. So by adding 4 standard deviation here, yeah, timeout interval here is covering more than 99.99 something percent of these sample RTTs. That is also saying, setting the timeout interval this way, there's going to be very few premature timeout in TCP. There, the timeout interval of TCP. The average plus 4 times the standard deviation. All right, good. Next topic will be the reliable data transfer. Okay, but we don't have time today, so we'll continue this tomorrow morning. With that said, I say goodbye. I see you tomorrow morning.